Here we're going to go through the solution of problem number 3 of the 1987 AP Physics C E&M exam. In this case, we have a circuit that has an inductor and a resistor in parallel, and those are each in series with a 10 ohm resistor, a battery, and a switch. So the first two parts of this are asking for the potential difference across the 90 ohm resistor and the rate of change of the current at the instant that the switch is closed. So for part A, for the potential difference across this resistor, we have starting off with Kirchhoff's loop rule. So with Kirchhoff's loop rule going clockwise from the battery, we have the potential in the battery, which is just the 20 volts, minus IR, where in this case R is 10 ohms, minus the other IR equals 0. Now you might wonder what's going on here. Well, at the beginning, since the switch has just been flipped, that would mean that this inductor is acting kind of as a brake. Any type of current that's going to come this way is going to induce a back EMF to exactly cancel the current that's trying to come this way at the beginning. So at the very instant the switch is closed, there is no current heading into this inductor. So after our loop rule, getting that being 0, the I going through here and the I going through here are the same. So now we can factor that out and we get this result. Now you might wonder, well, if that's the case, why didn't I just say, oh, R1 plus R2 is equal to 100 ohms and then just set it up as a quick series resistor? Well, because occasionally they do give problems where you need to determine I as a function of T going through either the resistor or the inductor. So you should be prepared to do that. And if that's the case, you would need to set it up starting from the loop rule. So in any case, plugging in our numbers, in this case we get 18 volts as the potential difference across the 90 ohm resistor. Now for part B, the rate of change of the current in the inductor. Well, in that case, we recognize that the inductor and the 90 ohm resistor are in parallel, which means that the voltage drop across the 90 ohm resistor is the same as the voltage drop across the inductor. So technically each of these is a minus. So we have a minus IR here and a minus L di dt over here. I canceled those minus signs and we're just going to isolate now for di dt. So we get the di dt is IR over L. Plugging in our givens, we now get a di dt of 36 amps per second. So yeah, at the instant that the switch is closed, yeah, there's no current going through the inductor, but there is a non-zero rate of change of current. It's 36 amps per second, and that's actually going to decrease as current starts to go through the inductor. So now, turning our attention to parts C and D. The switch has been closed for a long time, so part C, determine the current in the inductor at steady state and the energy stored in the inductor at steady state. Well, if the switch has been closed for a long time, let's see now. That means that the inductor is no longer giving us a back EMF. It's not resisting the flow of current to try to resist the change in the magnetic flux here. That has reached steady state. Now the inductor is acting like a wire, which means all the current is going to be going through here. None of the current's going to be going through the 90 ohm resistor. So we have a very simple application of Ohm's law here, which we'll just, for the sake of generality, do with our loop rule. The potential of the battery minus current times R right here, minus 0 because it's minus L di dt, but di dt is 0 here, and that just ends up giving us 0. So at this point, the current going through the inductor is 2 amps. So what about part D, the energy stored in the inductor? Well, hopefully you have memorized the equation for the energy stored in an inductor. I hope so. That would be U equals 1/2 Li squared. So now we plug in our givens, and that gives us an answer of 1 joule of energy being stored in this inductor. Okay, so now what about parts E and F? Well, in part E, we're saying that, well, parts E and F for that matter, at some later time t0 after steady state, the switch is suddenly reopened. So for the instant immediately after the switch is reopened, determine the potential difference across the 90 ohm resistor. Well, when the switch has been reopened, that means that there's only one way for the current to come out of that inductor. We have all of that energy stored in the inductor. But remember that energy stored in the inductor is going to be what's going to keep the current flowing. And that current had been 2 amps at the instant before the switch is open, and you can't just instantly change the current going through an inductor because you'd have that back EMF resisting that change in magnetic flux. So at the instant that you open the switch, there is going to continue to be 2 amps of current going through the inductor, which means that that current only now has one place to go. It's going to go through the resistor, and that resistor is, well, potential difference across a resistor, you know that, V equals IR, so you're going to get 180 volts of potential difference across that resistor. And then, part F, on the axes that they gave, sketch a graph of V versus T, where T is greater than T0, and T0 indicates the time at which the switch has been reopened. So here is our graph. Notice the labels on this graph. First, we label our axes. It does not matter what the units are on the horizontal axis, because what we really care about is the shape. However, on the vertical axis, we do need to label that point of that initial potential difference for the potential difference across that 90 ohm resistor. So they do like to have these types of numbers labeled if you know a particular number, especially at the start, or if you know the number for an asymptote or the value of an asymptote in terms of variables. They generally like to have that labeled. Also notice on the horizontal axis we have labeled our initial time as T0. So other than that, labeling our potential difference on as what we're graphing on the vertical axis, we are done with that part. So now let's see, where were the points awarded on this. In Part A was worth a total of 3 points. 1 point was given for calculating the equivalent resistance to be 100 ohms. We did that implicitly as a result of the loop rule. That is perfectly fine here. In fact, in a lot of ways, as I mentioned, this is better because this is more general. It would allow us to figure out I of t if we really needed to. And anyway, we got 100 ohms in this case. So then that was worth 1 point. The current of 0.2 amps, determining that was worth 1 point, and determining the final answer with units was also worth 1 point. For Part B, the points were awarded such that there were a total of 3 points in Part B as well. So first, there was a point given for noting that the potential difference across that inductor was minus L di dt. Well, we had a minus IR here, a minus IR here. I just canceled those ahead of time, but technically they are both negative. I'm sure that they would have given this point in this case because we did not do anything wrong here and we showed everything we needed to show. If you think that, oh, I definitely should have showed the minus signs, well, I could have simply said, how about we say that we're going to take a path going up here and a path going up here. In that case, there would be no minus signs. But in any case, what we really care about is di dt. We also needed to get that potential difference was 18 volts. Well, we calculated that right here. We didn't show that this comes out to be 18 volts. There was no need to for us, but at least showing something like this was also worth 1 point. And then the final answer of 36 amps per second with proper units was also worth 1 point. So next, moving on to Part C. Well, there were 2 points awarded here. The resistance here being 10 ohms as part of our calculation, that was worth 1 point. And the value of the current being 2 amps for our final answer was also worth 1 point. In Part D, there was 1 point given for showing the formula that U equals 1/2 Li squared, and then 1 point for plugging in the numbers and getting the correct answer with our units. What about Part E? This was worth 2 points. 1 point was for noting that the potential difference across the 90 ohm resistor was the same as the potential difference through the inductor, which was 180 volts, or for noting that that is a result of using Ohm's law and that the current is the same as what you had before going through the inductor. So 1 point for the answer and 1 point for either noting the parallel equivalence of voltages or using Ohm's law. And then finally, Part F was worth 2 points. You got 1 point for the curve decreasing in value and being concave upward, and you got 1 point for noting that the starting point had a value of 180 volts. And they also gave 1 extra point for obtaining 3 out of 5 correct units for your answers on parts A through E. So I guess in this case they were feeling sorry for people. Maybe the scores on this part weren't particularly good that year, so they gave 1 easy point. But that is how to solve problem number 3 of the 1987 AP Physics C, E&M exam, and also where the points were allotted. So if you have any questions, please let me know, and thank you for watching.